Hey class, I got a question here, and it goes back to our relativity chapter. Looks like a lot of you are studying and getting ready for the test. All right, so on relativity, special relativity, number 20 here, I'll read it here. It says, a moving rod is observed to have a length of 2 meters and is oriented at an angle of 30 degrees with respect to the direction of motion as shown in the figure. So by those words and kind of by the picture here, I'll just kind of draw. Here is a 2 meter long rod, and I'm going to draw it with a 30-degree angle as observed while it is moving, and the rod is oriented 30 degrees relative to the direction it's moving. And so one of these I tried to warn you about is be careful as you read this and say, all right, for the information they give you, who is doing the observation? So it makes it sound like to me that if we had our kind of standard, our S and our S prime system, the rod is in the S prime system and is moving, and the observer is in the unprimed system. Let me just double check that. So it's a moving rod is observed to have. So I think they're saying you are watching the rod move. And as you watch it move, you say it has a length of 2 meters. So the 2 meters is the length you observed as it is moving. So it is not the proper length, okay? It then goes on to say it's oriented at 30 degrees with respect to the direction of motion. The rod is moving at some speed of 99.5%, the speed of light. And then it says, what is the proper length of the rod? Okay, and then of course B, what is the orientation? Now, what makes this a little harder problem here, maybe I'll add some color to it, is the fact that there is an angle associated with it. So there is what you might call an LX, so the length of the rod in the X direction, the direction it's moving, and an LY, okay? So I'm going to go ahead and use this relationship that if you take the proper length and divide it by a factor of gamma, you get your observed length in a moving reference frame. And since gamma is always greater than 1, this is why we have the phrase length contraction. Things appear to be smaller. And they appear to be smaller in the direction they are moving. So, to find the proper length, let me write what is the proper length in the X direction, which is divided by gamma, and then this would be the length in the X direction. So in other words, I'm just going to take the components of it, and so no different than we did, any problem where we would break it down into its X and Y components. Now, there is no change in length in the Y direction because there is no motion in the Y direction. So the length contraction only has to do with moving in that motion. So what you might say is the proper length in the Y direction is the length in the Y direction in the non-proper, since again there's no motion going on here. So this is fairly easy to calculate. So I'll just say proper length in the Y direction would just be the 2 meters times the sine of 30 degrees, because to get the length in the Y direction, that's how I would do it. There's the hypotenuse, and I would go sine of 30 degrees. So that is the length in the Y direction as the object is moving, but again, moving and non-moving, so proper length are the same number, and sine of 30 degrees is 1/2, so we're looking at 1 meter for the proper length in the Y direction. So nothing real exciting about that. The more interesting one here is this gamma factor. And so we'll write that as 1 over the square root of 1 minus beta squared, where beta is the speed relative to the speed of light. So 1 minus 0.995 squared. So grabbing my calculator here, I will take this 1 minus 0.995 squared, hit enter. I will take the square roots of all of that, and then I will take its reciprocal. So this is about a factor of 10. And that means the rod appears to be 10 times smaller in the x direction. So let's figure out what does it appear to be in the x direction. And so that would be the 2 meters times the cosine of 30 degrees. Let's see, am I in degrees? I am, good. So 2 times cosine of 30. And so 1.73 is the length in the x direction as appears while it is moving. So its proper length is much longer than that, because this is the length in the x direction after it has gone under this length compression. So continuing on here and saying, all right, what is the length in the proper direction? I mean, in the x direction. What is the proper length in the x direction? I'm going to take factor of gamma and multiply by its length. So factor of gamma is 10, and it's 1.73 meters. And so that comes out to be about 17.3 meters. Okay. So I'll call that page 1. I'll move on here to page 2. All right, so in the non-moving reference frame, so if we were in the proper reference frame, it looks like I would have a rod that has a long length in the x direction, 17.3 meters, and in the y direction is still the 1 meter, so there was no change in that direction. So the hypotenuse here would be the length of the rod. So to get to that proper length, then I'm going to go 17.3 squared and a 1 squared and take its square root. Okay, so 17.3 squared plus 1 squared. Yeah. Oops. Sorry, that wasn't the 17.3. Let me try that again. 17.3 squared plus a 1 squared is 300. Square roots of 300. Well, it's about a 17.3. Makes sense. The 1 meter isn't going to change it by too much. I suppose if you want me to put 3.3, other than violating significant figures, it does show it's a little bit longer than the horizontal length, but basically something that is horizontal with, and you've got the hypotenuse of only 1 meter. It's not much longer here. So that would be the proper length. So there's the answer to A. And then a B, of course, is saying, well, what is this orientation angle? And so the tangent of theta is the opposite, 1 meter, over the adjacent, which is the 17.3. And so I will go inverse tangent of 1 over 17.3, and we're looking about 3.3 degrees. And so for the person who would be moving in the frame S prime, they would see something, of course, different than the other person. That was the whole idea of relativity. What would they see? And so this person here in the moving reference frame, getting the proper length, would see a much longer rod and at an angle of only 3 degrees. And then you could imagine, as it's moving relative to you, it goes faster and faster, it shrinks in this way, but not this way. So that would make the rod kind of appear to be shorter overall, but even angle up steeper and steeper and steeper. And so that's why we get, when it's moving, it's only a length of 2 meters total and is twisted at an angle of 30 degrees. All right. Hope that helped.